Okay, next step is to determine the departing variable. That is, it should be either x3 or x4 has to leave. So how are we going to determine this? Well, let's look back at the graph again, which is where our source of inspiration is. We have determined that we are going to go this way. We're not going to increase x1, we're going to increase x2. If we look at the graph, we want to stay basic. We want to stay feasible. So to stay basic is we got to be at one of these white or orange, white and orange, or just white dots. What a basic and feasible, then it's going to be one of the orange dots. Well, it's very easy to see on the graph that we're going towards that our next basic feasible solution is this one right here. But when we're sitting in the algebra in 300,000 dimensions, it's we cannot tell which one should it be, this one or that one. And so we're looking at what is the next basic solution that is still going to be feasible. We don't want to fall off this shape. We have a shape here that is solid, and we don't want to fall off it. This is where we have to live, because anywhere outside, we are lost. It's no longer feasible. So we want to know how far can we go and not fall off this shape. It's very important. If we ever fall off this shape, we'll be totally lost. If you think of it as 3 dimensions, as a diamond, you're traveling from corner point to corner point, from basic feasible solution to basic feasible solution, and the last thing that you want to do is fall off the shape. You cannot afford to fall off the shape. You can afford to select the wrong entering variable. You probably eventually get back on track. But if you pick a departing variable which results in a non-feasible solution, then the whole algorithm will end. So let's go back to our departing variable here. Now, so the calculations are going to have to be a little bit more complicated, not much. But what we do is, the first thing that we do is express basic variables in terms of non-basic variables. What this means in simple algebra is that we move all of the basic variables to the left-hand side of the equation. So we have equations here. We have x1 plus 3x2 plus x3 is equal to 16. We're going to keep x3 on the left-hand side, and we're going to move x1 and 3x2 to the right-hand side, minus x1 minus 3x2, and we're going to do the same thing for the second equation. So let's move there, and so what we're going to have is x3 is equal to 16 minus x1 minus 3x2, and we're going to have x4 7 minus x1 minus x2. We're also going to write our equation z as x1 plus 2x2. Now, the issue is x1 is going to enter. So what we're going to look at each equation, let's look at this first one, as x2 increases, goes up. So x1 is staying at 0, x2 is going to increase. What is going to happen to x3? As x2 increases, x3 comes down. And how high can x2 go? Well, x2 can go to 16/3. At 16/3, x3 goes to 0. So as x2 goes up, x3 comes down, and we want to keep x3 from becoming negative. In order to do that, we can only raise x2 to 16/3. At 16/3, we will have a 16 minus 16. We'll have x3 is equal to 0. That's from that constraint. From this constraint, as x2 goes up, x4 comes down until x2 is equal to 7. So according to this constraint, x2 can go as high as 7. But according to the first constraint, it can only go up to 16/3, just a little bit over 5. So therefore, x2 cannot go higher than 16/3. So when x2 reaches 16/3, what happens to x3? x3 goes to 0. So therefore, what this implies is that, sorry, that's not the implication. The implication from here, the implication from this argument is that x3 departs. What we're really after is we have to determine how high x2 can go. and it's the lowest of these, because if it goes any higher than that, then x3 goes negative. And therefore, the first variable of x3 or x4 to hit 0 is x3. x3 is going to leave the basis, because if x2 goes any higher, then x3 go negative. So x3 is the first variable to depart, and that is a departing variable.